Professor Cichos did his PhD in ultrafast spectroscopy at Technical University of Chemnitz in Germany. He was a Humboldt postdoc fellow at University of Bordeaux in France. Since 2007, he is leading the molecular nanophotonics group at University of Leipzig, and he is currently the director of the Peter Debye Institute for Soft Matter Physics. He has held visiting professor position at the University of Bordeaux and Princeton University. He contributed to the field of single particle photothermal detection. So he has developed several theories to understand the origin of photothermal signal, and also invented twin focus photothermal correlation spectroscopy. So title of his talk today is Physics of Photothermal Single Particle Microscopy. Fang, it's you.
Thank you very much, Subhasis, for the kind words. I'm actually not anymore the director of the institute, so this is good news at the end. Thank you also for organizing this nice webinar, which has been a great idea and collects quite a number of excellent talks. We've heard already one. So my turn is actually about the physics of my talk is about the physics of photothermal single particle microscopy. And what I wanted to do in the following is to highlight theories which have been developed to describe this photothermal signal and tell you a bit how it's modeled and what parameters are going in and what kind of different models you could apply to understand what you are actually seeing in the experiment. So Michelle had already nicely introduced that. So I may mention at the beginning that most of this work has been done by Markus Semke, who was part of my group a while ago during his PhD. He's now at the Fraunhofer Institute of Applied Optics and Precision Engineering, close by Leipzig in Jena, and coordinating the research there. So most of the thanks go to him, of course. So you've heard already that photothermal detection has actually a long history. As far as I know, even back into the 1980s, not only necessarily 1990s, and I call that macroscopic photothermal detection essentially. And it has been created actually to measure small absorption signals and to do absorption spectroscopy. And the spirit of all of these techniques is very similar to nowadays, except that all of these techniques have been using ensembles of tiny little absorbers that are finally responsible for the signal. So the spirit is that you have a kind of pump laser that is absorbed by the species you want to look at, and that absorber is not essentially only releasing fluorescence, but also releasing it through other channels, which are essentially heat. And that heat spreads in the environment, causes the refractive index change that you then finally probe with the help of a second laser, or you can do that even with a simple, the same kind of laser again. So the different techniques historically that have been invented involve a deflection of light here. If you modulate, again, your pump beam with a certain frequency, you come with a probe beam, and that is deflected by the refractive index profile you create, or you do a kind of lensing technique where you have this collinear alignment of pump and probe. Again, the pump is modulated again to reject the background with a lock-in detection scheme at the end, or you do some kind of interference technique where you just heat in a cell with a continuous pump laser your material, and the refractive index change is then detected in an interferometric regime. So the unique thing about that, and also about the single particle detection, is essentially that the absorption is not directly probed, but you use that secondary effect of the refractive index change in the environment to see what you have done actually. And this makes the whole signal generation process, of course, a little bit more complex than the normal fluorescence microscopy, and you've seen that nicely in the talk before. So what I'm going to do is not to review the history and the historical modeling of the ensemble photothermal signal, but rather the ones of a single particle detection scheme where you have seen already before the two versions essentially. So one's the differential interference contrast kind of way depicted here on the right side, where you start with again with the modulated pump beam, and you compare the signal with a probe beam between two different regions, and use that kind of signal then to feed into a lock-in detector to reject background and to measure actually what you're going to measure. And on the other side is what is meanwhile called the heterodyne imaging scheme, which you do in a collinear arrangement of the pump beam and the probe beam, and you can look at the probe beam either in the backwards direction, so some signal is reflected back from the sample and collected by the photodiode, or in the forward direction and then collected by the photodiode. So one is transmission, one is just in reflection. The analysis is going to work in the same way with the help of a lock-in amplifier that checks the modulation on the probe beam to get out a background-free signal, essentially. So overall, if we refer to this kind of setup in the following, the problem consists out of the following scheme. So you have a modulated pump beam that is modulated in intensity with some certain kind of frequency, and that is exciting your absorber, which could be a metal particle, but could apparently also be any kind of molecule that is creating this refractive index perturbation around itself. So everything is very small, essentially. And that refractive index perturbation, which is now modulated, is probed by a second laser that does not necessarily have to share the same focal plane. So everything depends apparently on the particle position within the pump beam and the particle position within the probe beam. So everything gets a bit more complex. So that is the thing we are going to look at. And there have been a number of theories developed to describe these signals. I may not have captured all of them, but the list is somehow described here. So one to describe the heterodyne signal, an equivalent dipole model, a generalized Lorentz-Mean theoretical model, a model which involves an analogy to a quantum mechanical scattering, so the Rutherford scattering model, Fresnel diffraction, and even Gaussian beam optics has been used to describe the signal in all of these its facets. And I have listed here a number of references. I apologize if I did not manage to capture all of it, but I hope you excuse that if I didn't mention your particular one. Okay, so what is the general setup which we need to understand that theoretically in a more general way, not specifically bound to any kind of absorber, but in a very general way. So first of all, the thing which is the origin of everything is a time-dependent heating, which we introduce by pumping an absorber with the help of this time-modulated pump beam. So this is the tiny little absorber here in most of the cases, and the experiments I mentioned for reference, it's just a gold particle due to stability issues and the ease of use, but it could be anything as a heat source. So that heat source is now, due to that kind of modulated pump beam, a modulated heat source where you have a modulation frequency, which is the capital omega, which is the intensity modulation of that system. And then there's an absorbed heat, or that kind of absorbed heat or dissipated heat, which goes into the environment, is related to the absorption cross-section and the incident intensity of your pump beam here. The IH will always refer to the pump beam somehow, or the pH. So what you then get is, of course, the heat diffusion into the environment, and it creates a time-dependent and spatially dependent temperature field. If you look at just the point heat source, where the heat source is really tiny as compared to the thermal diffusion length, which is defined here on the right side, I just say a few words to that, then you see this kind of temperature rise in the environment. So it scales with 1 over the distance here, which would be the stationary solution of your heat conduction problem. But due to the modulation, you get this kind of additional term inside, where this very much looks like a wave, but of course there's no temperature wave. And so this is a kind of distance-dependent phase shift of your modulation, if you want to speak like that. And most importantly, there's also an exponential cutoff to that. And the exponential cutoff is given by the thermal diffusion length. And that thermal diffusion length is again here on the right side. It's just 2 times the thermal diffusivity divided by, so the thermal diffusion coefficient divided by the frequency of your modulation, right? So the radius until, or the distance to which it can diffusively propagate is set by the time scale essentially of your modulation. If you have a high frequency of several megahertz, the diffusion cannot propagate through all space, and then you just get a stationary profile. We will see that in a second. So thermal diffusivity is given by thermal conductivity, which is the kappa here, which you also see here, divided by density and specific heat capacity, right? So this would be the kind of screen solution. I called it screen because it has this kind of exponential screening term here, and that is valid whenever you have essentially a fast heat diffusion or low frequencies or high frequencies. If you have low frequencies, so that means the diffusion of the heat can propagate over large distances, which are way beyond the length scale you are probing. You can probably assume, or you can assume also a temperature rise in space, which is given by that without the exponential term, because then the distance here r is much smaller than this thermal diffusion length, and you can just set that to 1. So that are the differences which appear. So this is just a time-dependent heat source, and here's just a picture that should kind of illustrate that what I just said. In principle, you create that 1/r long-range temperature profile, which is shown here. Actually, in the color scale is the temperature rise in a log scale, so just that you see that. And on that axis is the time, and on that axis is the distance. You see that you can cover large distances here. The white line is actually the thermal diffusion length, this RTH, when omega is just 100,000 inverse seconds here, right? So it's a large distance the heat can diffuse. And if you look at the temperature profile, you see here that over a length scale of 1 micrometer, or here it's 2 micrometers, the temperature is really completely modulated. So the little bit transparent curve here is the unscreened solution you've seen before, right? But if you crank up the modulation frequency, that omega, to about 10 million inverse seconds here, your thermal diffusion length goes down to only a few hundred nanometers, or 168 nanometers. So it is already in a range where it's smaller than the beam waste, for example, of a Gaussian beam. If omega 0 is here the Gaussian beam width. And so that means here on the outside, the temperature profile is not anymore modulated. You just get a stationary profile, and everything is happening in between here. So there somewhere is the exponential screening length, actually, which dams all the oscillations here of the temperature profile outside. Yeah. So yeah, you have to think about that. And this is also opening possibility to measure, for example, thermal conductivity, because that screening length here changes then. And that overall translates now into this refractive index change, which is given then finally by the refractive index of the environment times the refractive index modulation contrast you have here, and this kind of time-dependent factor, and also, of course, here inverse distance dependence. And that contrast you gain is proportional to the thermal refractive index or coefficient. Michel already mentioned the dN by dt, which is typically negative because most of the materials upon expansion just decrease their refractive index, but they are very small. So they are on the order of 10 to the minus 4 per Kelvin. So that means here you expect small changes in the refractive index overall. But besides that kind of thing, that refractive index change, there's now also a back action on the absorber. So if you in particularly think of a gold nanoparticle, then a gold nanoparticle shifts its plasmon resonance if you embed that in different media of different dielectric contrast or constant or dielectric or refractive index. So if you change now in the environment the refractive index, you will also be able to change the polarizability of the actual absorber in a tiny little bit, and that also plays a role in some of the cases I'm going to show you. So you can model that as a delta alpha, so a change in the polarizability of that object with the refractive index of the environment that is then created by the chain or by the temperature here, and the temperature rise to the thermorefractive coefficient at the end. So overall, that gives you then here refractive indices or refractive index profiles now, which are over log distance here, but this is linear for the same kind of frequencies, where you see on the left that the response you get for low frequencies is similar between the screened and the unscreened temperature rise, because you hardly see the other curve. But here in that case, you slightly see that the unscreened solution is probably not anymore good for your description of the signal, and both curves deviate from each other. And you also see that here at the tail, there's hardly any kind of modulation. So again, this kind of line is a typical probe beam size of, let's say, 250 nanometer radius, or beam waist in that case. So this is the refractive index change you create, and that is the signal you actually detect together with the modulated polarizability of that absorber here. So overall, everything looks rather complex. Again, the modulated heating, which creates that kind of refractive index profile, and the probe beam, and in that they both can have a certain focal distance of each other. So the shift of the focal plane of the pump beam and the probe beam is here in that example delta ZF, and throughout the talk as well. And you have a particle position with respect to the probe beam focal plane, which is always called ZP here in that case, right? So you take that kind of refractive index then and do some kind of scattering calculation, and that scattering calculation essentially leads to a scattered electric field that is, of course, superimposed to the incident electric field, which was the background field in Michel's talk, which gives you a total field. And for that total field, you calculate a pointing vector. And in many cases on models, just that kind of interference term survives, as you've seen earlier. So everything is linear in the incident field strengths overall. But so in some of the cases, we also take the full pointing vector, which we then integrate over a certain angular domain, because that will, or is certainly important, that's the scattering problem. So if you take the whole solid angle, your change in the scattering signal will go to 0, because the energy has to go somewhere, and it's not lost, except there is some additional absorption appearing suddenly. So, so what you have to really take into account is not only finally the illumination aperture of your microscope, which is carrying the pump and the probe beam, but also the detection aperture, which is either in the forward or the backward direction. So what I will talk about is essentially the forward scattered signal, because for the backward scattered signal, there's still no really quantitative consistent theory around, which might have its origin in the fact where the actual back reflected signal comes from originally. So overall, the signal, which is then coming from the photodiode here, is PD, and it has a certain modulation amplitude, which I call delta PD. And that is measured in amplitude and phase with respect to the original modulation. So at the end, I will always refer to a relative photothermal signal, which is the detected signal with a refractive index switched on, minus a detected signal without this kind of refractive index profile relative to the incident power. So this will be the delta PD over the incident one. And that can have, as I said, a phase, and I take the phase into two components. One is the so-called in-phase component, because it has the same kind of phase as the incident modulation. This is all the cosine part here, because the modulation was cosine. And there's also an out-of-phase, which is the sine squared here. You obtain that from the log-in detection by just projecting that kind of signal here onto a sine or a cosine function and integrate over that. So this is the way you obtain a signal even in a calculation, right? So just to highlight some of the features, and that this is really different from what you typically observe in fluorescence detection. Here is some example. The left one, an experiment we did at zero frequency. So there's no modulation of the pump beam at all, except that you either switch it on and have it continuously working or switch it off. It's just a gold particle which is embedded in a polymer. So it's just fixed. It has a 30 nanometer radius, and you have a certain detection aperture. So you measure once with a probe beam, the scattering, you get this kind of signal. So this is the optical axis direction. And you switch on the heating beam, which is at 532. In that case, you get this kind of signal. They essentially look the same, which they should, of course, because there's only a tiny little difference. So here you see an actual cut. This is this one which is here, where you have here a positive signal, and one you have a negative signal. So if you take the difference of these two, you get this kind of dispersive signal, which is very characteristic for the photothermal detection technique, which is just coming from the fact that in one case you have just more signal than without the refractive index profile. In one case you have just less. So overall, your focal volume is not just a single blob, it's just composed in general out of two blobs, which can change in size. And the question is on what does that depend and how can you adjust that, and all of these things. So what is in addition in here, so the dots are actually the difference between these two channels is the modulated photothermal signal with a frequency of 300,000 inverse seconds. And you see that it's exactly the same because at this limit here, we just have a thermal diffusion length, which is much, much bigger than the probing size of our probe beam. And therefore, we can the omega equals to 0 signal. So this will be just true, and the N of R will just be the refractive index profile of the stationary solution there without any kind of time dependence. But as soon as not anymore true, so you have this kind of thing valid, you have to use here the effect, the exact refractive index profile in space, and that will become important. Okay. So what are now the models which describe the scattering in an electromagnetic framework or electrodynamic framework? I'm probably too slow. So I want to go into at least at different depth into these different models here, which are not necessarily historically in the right order, but in terms of complexity fit in this way just nicely. So one of the first models have been this effective dipole model. So you replace refractive index perturbation you create in space, which is in general long range, I have to say, by an effective dipole. So from that, it already becomes apparent that you do some kind of Rayleigh scattering approach. And that kind of Rayleigh scattering approach will only be valid if the thermal diffusion length at a certain frequency is much smaller than the probe beam size or the wavelengths of that. So that perturbation should be small. Otherwise, in the same way as you cannot treat a large particle with Rayleigh scattering only, you will run into problems. So you replace it by a single dipole, and the dipole here is described by a slight variation in the dielectric function within a tiny little volume multiplied with the incident field, and you can resolve that delta epsilon here into this kind of expression. And by definition, this kind of expression should be the same as epsilon, which is epsilon 0 times epsilon r, times a polarizability of, which is an effective polarizability of the dipole multiplied with the incident electric field, right? So this is the dipole you create. And if you take the dipole now with the alpha here, with the alpha term, and connect it to a Gaussian probe beam, which is the part here where all the GUI phase is inside this prefactor here, you get this expression for the dipole, and then finally this expression for the scattered electric field. So this is the ES, which you have to put into your total electric field. And when you just say that the incident field times the electric field of the scattering survives, then you just calculate this kind of signal at the end, which leads you finally to an expression for the total photothermal signal, the relative photothermal signal I showed you earlier. So at some point in between, you might be tempted to say this dipole is proportional to the refractive index of the medium times the perturbation, but it turns out that if you write it here in this kind of way, the alpha n is proportional to 1 over the refractive index of the medium. And so the n0 here doesn't play any kind of role, but what you find is that the figure of merit of the photothermal detection at the end is the thermorefractive coefficient multiplied with 1 over kappa. So the heat conductivity plays a role, because if you have a large heat conductivity, the temperature close to your heat source, the temperature rise will be small. If you have a low thermal conductivity, it will be high. So overall, that gives you the following kind of dependence here. So this is the total signal you can sort out with the help of the Gaussian beam, and you see two kinds of things, essentially. I would say, first of all, the signal is dispersive. That is coming from the Gaussian beam and essentially from the GUI phase inside. So you have the ZP, which is the particle position. ZR is the Rayleigh range, so the depth of focus of the Gaussian beam. And the ZP is creating that kind of dispersive signal. And the second thing is that overall, this is an out of phase signal. It's only, so the model gives you only an out of phase signal that is proportional to the dN by dt, again, the absorption cross section, the pump beam power, but the frequency dependence is in the thermal diffusion length, which was going like the square root of 1 over the frequency. So overall, this kind of model gives you an out of phase component which scales as 1 over the frequency of the modulation in the pump beam. So that is maybe a short summary. So you only have an out of phase signal. It's actually valid only in the high frequency limit, where the thermal screening radius RTH is coming into play and is on the order of your probe beam size, and it creates the dispersive signal due to the Gaussian beam probing at the end. Yeah? So these are the things which come out of that kind of symbol model. Then originally, I think historically before, there was the heterodyne detection model laid down earlier, which is a kind of extension, and on some scale also a step back. So first of all, it takes the full refractive index profile into account and models the whole process in terms of a vector Hertz potential. And essentially, you don't have to know what a vector Hertz potential at the end is, but it translates the refractive index profile and the polarizability profile you create into a light source. So I've not written down the theory, which is actually in that paper by the group of Brahim Lunis, but I've sketched it in a different frame. So what you're dealing with is in a scalar theory, the inhomogeneous Helmholtz equation. It's inhomogeneous because you have that refractive index profile here inside the Helmholtz equation. So you can approach that in different ways. And this kind of theory approached it in a way that it created the homogeneous one here, where you don't have the refractive index profile, and all of the N of R stuff is put as a light source, so to speak, here on the right side. And that's in that kind of scattering potential F. So that scattering potential F obtains or has the refractive index profile, and it's even only taken to the linear order in the delta N here, the refractive index change, because you have to square this kind of guy here, right? And then this is solved And what you obtain is now a more complicated signal, but it's solved for the scattering of a plane wave, essentially. So there's no focused beam, no Gaussian beam, which is probing the refractive index profile, but there's a kind of plane wave probing only. And the argument was just that the Gaussian beam is essentially in the focal plane, a plane wave. So what you get is at high, or that kind of diagram, which has actually been calculated in a different way, but essentially it corresponds to the early findings. You get a frequency dependence of your photothermal signal, and now you get an out of phase and an in phase signal. And you see that the out of phase signal, the sine signal here, at high modulation frequencies, so beyond 1 here, below 1, this is the wave factor multiplied with RTH, so it's RTH over lambda essentially, scales again with 1 over the modulation frequency. This is what you've seen earlier already. So this is this kind of blue points from an experiment, and this is the out of plane, the out of phase signal here. But there's also now an in-phase signal, which is new now in that model, and that in-phase signal scales as 1 over the modulation frequency squared for small thermal diffusion lengths. But then here, for larger thermal diffusion lengths or lower frequencies, the signal diverges with a logarithm here. So it actually goes as the logarithm of k times RTH for low frequencies. So if you go with your modulation frequency to 0, you essentially end up with a divergence. So in that kind of model, there's no dispersive signal because there's no Gaussian beam which is probing that. So it cannot explain the dispersive signal at all, right? But you can take that approach here and entirely bit extend that, and the way to extend that is actually coming from quantum mechanics. So you probably all of you had heard of an experiment of Rutherford where he scattered alpha particles on atomic nuclei, and these alpha particles in a quantum mechanical way can also be described as waves. So you scatter waves essentially on a Coulomb potential, and that is the quantum mechanical Coulomb scattering, where you see here the Schrödinger equation on the right side with the interaction constant, where C is just the force constant of the Coulomb interaction. So there's the 1 over R potential, which is inside. So you can write down now your photonic problem, which was introduced before also in the Helmholtz equation, which is equivalent to the Schrödinger equation, where you have the same kind of structure, only the nu here has to be replaced by the refractive index contrast, the size of the scatter, the wave factor, and the background. And you can take advantage of all of the solutions people have obtained over the years here for the Coulomb scattering in quantum mechanics to obtain a plane wave solution. And what you do then is take many of these plane wave solutions and put them into a wave packet in space. So you can take plane waves and amplitudes of different k vectors to create a wave packet in space, which is your Gaussian beam essentially, right? And if you take many of these here, put them into this wave packet, you can propagate the wave packet over time and see how this wave packet is actually scattered on this Coulomb potential or Coulomb-like potential. And this is what you see here. This is a result of a simulation we have done. So this is the wave packet essentially here at a certain state. Here sits the gold particles. So this is distance. And you couple in, like in a scattering problem here with a certain beam parameter or scattering parameter, which is a certain distance from the actual optical axis here. In that case, you see the wave packet is bent here by the refractive index profile around that gold particle. While this is a limit for very short wavelengths in principle, so more or less the ray optics limit, this is the full wave packet which is scattered, where you also see that kind of deflection, but it's due to the extent of the wave packet much harder to see, of course, right? And you can prove that kind of deflection even in an experiment very easily if you just take a quadrant detector as your photodiode and either take the full signal or certain differences between left and right, top and bottom, who are here in the Z direction. So you see how the actual beam is deflected to one or the other side. And that allows you to get even three-dimensional resolution where your particle is in a Gaussian beam with the help of this kind of deflection technique, which is actually in other systems, like in optical tweezing, very common, for example. So this is a great advantage which you have here in the photonic Rutherford scattering. So, but as you know,
So
for the classical
5 minutes more.
5 minutes more. Okay,
Yeah.
and I really have to hurry up. You also have a classical analogon. So between the quantum mechanics solution and the wave solution. So they are completely equivalent for the classical Rutherford scattering, and so it is also for the optics. So if you look at on one side on the mechanical problem and on the optical problem with Fermat's principle, you get the same kind of solutions because the structure of the equations is actually the same, and that's the way we conducted here this kind of experiment, which is a nice demonstration experiment, at least for students, where you do this kind of heating of a macroscopic metal particle and a scattering of a second beam, which is actually the helium particle, so to speak, in our case. And then you measure the deflection angle, you nicely see the original result obtained by Rutherford earlier ago, and you can even see that by eye. So since I'm in a hurry, I probably will skip that kind of part or just mention it shortly. That kind of experiment I showed you brings you readily to the idea that you can treat everything also in a simplified approach, which is an ABCD matrix optics approach, essentially. So you take a Gaussian beam, characterize that by the beam parameters, and represent your system as a kind of thermal lens. And that means you extract from that Rutherford experiment some effective focal length. So if your light beam goes in like this here, you have that kind of focal length. If you are a bit closer, then you probably have a shorter focal length. And if you capture from that an effective focal length, which you see here, you can describe that by matrix optics techniques. So you create some free space, a lens, some interfaces, and then some detection. And from that, you get a photothermal signal, which captures actually most of the things we've seen before. So the photothermal signal depends on the heating beam intensity profile, the detection beam intensity profile. So that transfers, for example, the infrared resolution into the visible region with that kind of component, and also gives you the figure of merit where you have the thermal refractive coefficient and the heat conductivity at the end. So that works also in the experiment. You can show that it nicely works if you have a nice Gaussian beam. If you don't have a nice Gaussian beam, then it doesn't work that nicely. So let me come finally to the most advanced model, I would say, which takes everything into account which you can think of. This is the generalized me theory model, where you solve everything in a me framework, but even describe the incident pump and probe beam in terms of a series of functions with the help of beam shape coefficients. So me theory is in general for plane waves. Generalized me theory is even developing the incident field of a beam into a series. So we can really model with the help of that all the aberrations which are even present in the experiment. So you see a comparison of the pump beam and the probe beam in space. We can now measure the signal, calculate the signal, and essentially what you find out is a simple truth that everything on the small scale essentially behaves like a divergent lens. So depending on where you place the divergent lens, which is created by the refractive index profile with respect to the focus, is giving you a different signal shape here in that kind of setup. So maybe I skip also that here. This is the experimental proof that it really works accurately, 100%. and go to this kind of slide, which is mainly the last slide, where I compared it to the heterodyne model, which did not include this kind of Gaussian beam probing. And the main thing you should see here between these two diagrams, so this is the high heterodyne, and this is LMT, so the generalized mean theory, is that this divergence of the beam disappears, which is the in-phase component. So it's not anymore divergent. Your total photothermal signal will saturate at a certain point at low frequencies, low modulation frequencies, and the out-of-phase component, which saturated before here in that model, actually goes down. It has a maximum, which is coming out of that, and you can even understand why this is like that here for the out-of-phase component. So in general, the diagrams you obtain with the exact theory are actually looking quite different from the ones here, and only a few things are still captured, but the individual components have a completely different frequency dependence as you've seen before. So with that, actually, I'm at the end. So I just covered these different models, and the main thing you should keep in mind is that, of course, you can choose any of these models depending on what you want to describe, but mainly everything works more or less like a divergent lens, which you create dynamically, and that gives you the signal. And I did not cover any kind of optimal detection aperture, spatial resolution limits, sensitivity limits, or the phase transitions. All of that can be included in the generalized mean theory and be calculated. And with that, I think I'm at the end. I just also want to thank the group, which always suffers if I do other things than taking care of them. So thank you also very much for listening. Happy to take questions.
Okay, thank you, Frank. And yes, you can ask a questions. You can write in a chat, or you can directly ask.
I have a question.
Yes, go ahead.
Actually, you have described several models, theoretical models. Have you considered applying Gupta's and co-workers' theory of photothermal spectroscopy? Do you think that is it applicable for nanoparticles?
Then I first would have to know what it includes in detail. I'm sorry, I can't remember that, but maybe you can tell me about. I mean, I think
essentially Gupta's theory, if I remember correctly, it involves two steps. One is evaluation of the temperature gradient in the sample by the action of the pump beam. Then that changes the refractive index. Then the incoming probe, either visible beam or any beam, that gets deflected or is scattered. Then one can evaluate the scattered intensity or as detector or the transmitted intensity. So if the sample assumed to be a very small size, then like a nanoparticle, then my belief is that Gupta's theory is also applicable in this case. Do you agree with that?
I think I agree with that. I mean, essentially, all of the models I presented are doing something like that, right? They model
that's right.
In a different approximation, that kind of refractive index profile, as compared to an ensemble experiment, where the shape of that refractive index profile is essentially the shape of the pump beam. Here, it's created by this inverse distance law, which is very important. I mean, so you have an inverse distance law, which has in principle no length scale, and the only length scale you introduce is the one of the probe beam. In the case of an ensemble of heaters, this is already set by the amount you're heating and the shape of the pump beam in space.
The other one question, a quick question,
yes,
that you mentioned in one of your slides. What is the physical meaning of that equation?
Of which?
The figure of merit that you mentioned.
These are the two components which are everywhere in the signal. So if I randomly take out one of the the slides here, maybe just let me go back to one of the equations, which is nice enough to show you, probably here. Let me go back, this one, right? So you see that in all of these equations you get, you essentially have the this thermal refractive coefficient and the heat conductivity which appear, right? Which determine the size of the signal. So if you could increase that or decrease that, you would get a larger signal, of course. That is what it says. So that's why I called it a figure of merit, because it defines everything from the material side. But of course, you can also increase the pump power, which you probably don't want, or you can increase the probe power, but this is a relative signal. So for the relative signal, it doesn't really matter at the end, the probe power.
Well, thank you.
So that's why I defined it as a figure of merit. So, as shown in the previous talk, if you can enhance the dN by dt, for example, by phase transition, then this is a good thing and increases the figure of merit.
Yeah, it essentially says that the signal is proportional to two terms. That's very interesting.
No, not only. I mean, yes. I mean, these are material terms which you can influence. All of the other terms, like for example here, the beam waste or something like that, the wavelengths are properties.
Yeah, but you can all fix some of them can be fixed. Then it becomes that this is proportional to these two terms, right?
Sorry, I didn't get the question.
If ZR and ZP and R at omega 0, if are all fixed, then your signal is proportional in a sense the refractive index gradient and the thermal conductivity, right?
If all the rest is fixed, you can say it like that.
Yeah, that's interesting observation. Thank you very much.
Okay, we go to second question, I think from Eduardo Maya Paiva. So can you please ask?
Hello, Professor Frank. Nice presentation. I would like to ask you about omega in the modulation frequency. Is the bandwidth of the pump pulse, or is the repetition rate of the pump modulation?
So in the model I presented, it's actually not a pulsed laser, but you can view it as you want. So the pump power is modulated by that kind of frequency. So if you would have a repetition rate, of course, with short pulses, then I assume that you're not creating only one modulation frequency, but have a whole spectrum of modulation frequencies which are present, and then you probably create signals also at different frequencies where you don't even detect, right? So if you have a time harmonic heating in this kind of way, and you can detect just at that frequency, then this gives you probably the maximum signal you can get, and you don't have to spend any kind of other detection frequencies which you are not detecting anyway. So is that answering your question?
Yeah. So there is some practical threshold about this frequency.
Practical threshold, and how do you mean that?
I mean the pump pulse bandwidth could be not too large, right?
Yeah, so that's what I mentioned here. Maybe too briefly, what a high frequency introduces is a cutoff of the modulation. So you see that kind of modulation term here in the temperature, and if RTH is very small, then you essentially damp this kind of oscillation in your refractive index, and that's what I wanted to show you here or here. So if you look at that carefully, you see here nothing is really oscillating in this distance region for high frequencies, while it is doing that still at low frequencies. So the higher you create the frequency, the closer you come with that kind of exponential cutoff to your particle, and at the end only a tiny little fraction around your particle is modulated, but that happens at 100 megahertz or so when you're really close. And that will finally also leave at high frequencies only, I think, a scatterer, which is modulated. So this plateau is essentially nothing else than the modulated polarizability of the particle, finally.
Okay, thank you.
I have one more question, if it is okay.
Sure. I mean, Subhasis, it's yours.
Okay, yeah, I think then this will be the last question, and then we close.
Okay.
You said that the pump beam is modulated. I think it's in megahertz range, if I'm correct.
So most of the time we use 300 kilohertz around that, but for thermal conductivity measurements, for example, we go to 5 megahertz, up to 5 megahertz. Actually,
if it is in megahertz range, then do you have any overheating of the sample? Because that's a very high frequency, right?
You mean from the high frequency? I mean, we are certainly heating the sample, but the heat source and the coupled heating power is tiny as compared to what you can transport away to infinity, and that's a precondition. I mean, if you have a large object where you put in a large amount of heat, the whole sample will of course heat up, but this is a tiny little particle, essentially a point heat source, which takes up a heating power of, let's say, a few 10 nanowatts finally.
Okay, I think we will end the webinar. So thank you, Michel, again, and thank you, Frank, again, for the nice talks. And thank you all for participating in the webinar. And so there will be the second webinar in the next week on Wednesday at the same time. Okay, then see you all.
Thank you very much, Subhasis.